So I think most of the people here in this audience have been to most of the talks in this session, so you know, roughly speaking, where string theory is headed. And there's one of the things that I guess I'll pick up from, which hopefully most of you went to, maybe Kumran Wafa's talk, which is why is it useful to look for a unifying principle for all of the backgrounds of string theory with a specific supersymmetry, for example, n equals 8 in 4 dimensions, or n equals 4, n equals 2. He was talking about n equals 2, and there's been a lot of work recently on n equals 2 gauge theories. And Laura the last session, you just heard all about n equals 1 string theories. And it's useful to kind of begin with places where you have extended supersymmetry, because that, by dimensional reduction, you can very quickly pull up to 10 dimensions or 11 dimensions, and the theory is much simpler. So there's hope that if you have a unifying algebra, you learn something about the fact that we've got all these dual string theories, and why do we have such a multiplicity? It's we understand why we have a connection between string theory and real particle physics, but why do we have dual string theories? Why do we have heterotic type 1, type 2b? We'd like to kind of engage them together. Then we have F theory, we have M theory just waiting. And if you're, for example, a supergravity theorist, you churn out so many solutions. So I mean, Eric Bergshoff is talking in the next session. And it's just there are so many supergravity solutions, and there are so many brane solutions, that it becomes incredibly confusing. I mean, Lara told you about all these disconnected components of moduli space. So you want some principles which unify and help you organize the theory a little bit better. And I want to the first 5 slides are actually work that dates with Kremer and Julia in 1980s. But it's, and particularly this paper by Peter West in, the other one, sorry. Peter West in 2004, and he'd been working on this for quite a while, but where he comes up with this conjecture for 32 theories, string theories, and 11-dimensional supergravity. So you've got 10-dimensional string theories and 11-dimensional supergravity, and these are all theories with 32 conserved supercharges. And he was able to show that you can deduce the common global symmetry algebra and map that to a particular specific algebra, which is an algebra known as E11, and that's rank 11. It's kind of a series due to Kremer and Julia, and it goes up from, it starts with E8, which I hope most of you know of. It's just an affine Lie algebra, okay? And then affine E8 is E9, which is rank 9, and once you get to E10 and E11, the main thing that changes is that you have real roots and imaginary roots, and the representation theory of the Lie algebra is extremely complicated. But it's still a generalized Casimir Lie algebra, and I'll try to explain to you why it's useful to at least know something, which is a starting point. And then, starting from his work and what he had started to do with his student Schnackenberg, I was able to pin down what happens for 16 supercharges. And for 16 supercharges, you have the symmetry group D11 cross E8 cross E8, where that's affine E8 cross E8. And then, as I said, I'll have very little time to probably talk about my own work, but I wanted to at least get started. We'll just see how this goes. Let's see how much time we spend. So I wanted to just explain the basic idea. The basic idea is you've heard all about T dualities and S dualities, strong weak coupling dualities and target space dualities, okay? And those are the most fundamental in string theory. Then, when you come to n equals 2 or n equals 1 gauge theories, there are many other, you heard the word duality repeatedly in various talks. But these are the more fundamental ones. And the basic idea is that you think of it in terms of dimensional reduction. So you start with 11-dimensional supergravity, which, if you rearrange the fields, is almost the same thing, mass is field content, as type 2a 10-dimensional supergravity. Each of them, and the 10-dimensional supergravities, type 2a and type 2b, have string theory extensions, okay? And then from there, we get to theories with n equals 1 10-dimensional supergravity, which is unique, and it's the one that's common to type 1b and the heterotic string. So I'm going to try to organize all of that with an algebra, okay? Which is great, because we've got the 11-dimensional guy and the 10-dimensional guys, and they're all pinned in together. Okay. Now, the way you do that, and this is a procedure that people have known for many years, especially in supergravity and in algebras, is you take all of the fields you start out with in higher dimensions, the 10-dimensional, 11-dimensional theories, and as you compactify them on tori, on circles, you dualize all of your additional p-form fields, the Nova-Schwarz and Ramon-Ramon p-forms, to make them scalars. It's just a process by which you dualize them. So you maximize the number of scalars, and the scalars define a group manifold for you. And so if you go down to 7, 10, 9, 8, 7, 6, 5, 4, 3 dimensions, you get to E88, okay? Now to go down below 3 dimensions, you hit a problem that in 2 dimensions and below, you can't dualize, you can't distinguish a scalar field from a gauge field. And so this procedure no longer works, but string theorists know how to do this. And so in fact, when I was a postdoc with David Lowe in 1995, we worked on type 2A heterotic 6-dimensional effective string duality. And compactifications to 2 dimensions, you could fit them very neatly within the monster group. It's just that the monster group is a rather large group, and it was not clear whether we could do better than that. You want the minimal group that's adequate to do your job, okay? So you keep looking further, and then, as I said, several years pass by. There's another paper that was very influential, which actually was the reason why we worked on this, was due to Greg Moore and Jeff Harvey in 1995, where they actually went right to n equals 2 heterotic string in 4 dimensions, which, as you know, is a very complicated theory. It has a lot of phenomena that were not known at that time. But they studied the algebra of the BPS states, which in a heterotic string, you can write down the vertex operators and just calculate the vertex operator algebra of the BPS states. And they conjecture that it was a generalized Kac-Moody algebra, but the details were never worked, it's partially worked out. It's a very complex problem, and this problem will have to be redone, and filled in and completed because it's very exciting. But they found many interesting features. They found hints of E10 already embedded in both the gauge and supergravity sectors, but it's a completely different derivation from Peter West's work, so I'll come back to that. And they had this concept, most important is the conjecture, that the multiplicity of low-energy effective dual string and field theories should be understood as realizations, different realizations of a generalized Kac-Moody algebra. That's what Peter West does for 32 superchargers. Okay, so the conjecture is already in there in 1995, and Peter eventually solved this problem with his student Igor Schnackenberg in 2004. So he started in 2000, as I said. He already conjectured that M theory is the group E11. Now, what does that mean when you just say a theory is a group or a theory is an algebra? Well, he meant it in the sense of nonlinear realizations, which is what I just told you about, the dualizations to scalars and so on. But another way of thinking about it is just to say, well, suspend belief. I'm not interested in, I just want to know first, I want to know whether you've convinced me that you've arrived at the correct group or the correct algebra. And then we'll think about what realization we choose of that algebra. That's the way an algebraist thinks, right? You first identify the algebra, then I can find free field realizations or matrix realizations, or who knows, somebody might come up with some other way of realizing the algebra. So it's important to first pin down the algebra. If you can do that, that's great. That's really beneficial. If you can derive that from the vertex operator algebra, as we said, do what Moore and Harvey were doing and complete it, that would also be great, but that's very difficult because the n equals 2 theories have so much dynamics going on. It's extremely difficult to complete that problem. Okay, so this is what Peter West did, was he took each of these theories, 11-dimensional supergravity, 10-dimensional type 2A supergravity, type 2B supergravity, and the massive type 2A theory, which has Roman's mass term, a cosmological constant in 10 dimensions. And these are, by the way, if you map just to string theories, this covers the full spectrum of D-brane charges, for example. Okay, so that's basically what's being done here. But he just has to identify the global algebra working with the supergravity, and that's adequate to answer this problem. And as I said, what he showed is that you take each of these theories, you write down a basis of generators for their global symmetry algebra, including all of the p-form potentials that you have in there. And then you match that, map that, show that it's isomorphic to E11, the generators of E11. And once you've done that, that's really wonderful because one theory, the 11-dimensional guy, has 11-dimensional Lorentz invariance. The other 10-dimensional ones have 10-dimensional Lorentz invariance. And type 2A and type 2B, from the point of view of a Dinkin diagram of E11, which is rather simple, it's just E8, and you get to the 8th node. And then there's a bifurcation. You can either go here, and this he identifies as type 2B, or you continue on, this is 2A, And then finally, there's one extension. There's a central charge extension, which only exists for the 2A theory because it's non-chiral, and that's massive 2A. So it's this observation. It's just playing with these Dinkin diagrams and noticing that you can embed the Lorentz algebra, which is A9, in either type 2b or in type 2a. There are two ways. There's a bifurcation of this node. And then 2a is the only guy that has the massive extension, which a supergravity person will immediately tell you, well, that's because it's a non-chiral theory. So that's why you have a central extension, whereas 2b does not because it's a chiral theory. So that's the basic evidence. And after that, it's a matter of just working it out. And they do that using the method of nonlinear realizations. And Schnackenberg and West, in a series of papers, they just enumerate all of the generators, keeping only the volume preserving part. This is a small technicality. You keep the SLDR. This is something all the dimensional reduction people do. The volume of the space kind of gets hidden. And if you stick with just the volume preserving generators and add to them all of the supergravity potentials, including the dilaton axion when you're doing the 10-dimensional theories, then you calculate the algebra, compute explicitly the structure constants, and you've got a result, and then you identify it isomorphically from each of them to the Chevalier basis of E11. And if you've done this, you've got a unique determination of what the algebra is for 32 theories with 32 supercharges. And this is really marvelous. I mean, I was really excited when I saw this paper because it's such motivation to get going to the next problem, which is the theory we'd really like to do, which is when we put in Yang-Mills fields. So just to finish this up, this is just the details of it, and I'll go through this quickly because it's much more useful if you read his papers. And if you want to learn about very extended algebras, the best paper to read is by Gabriel, Olive, and West. It's a great review paper, and it covers and explains all of the group theory excellently. It's very good. There's also a couple of papers by Kremer and Julia which explain all of this, dualization and so on. And Peter West papers, of course, which again explain all of these algebras. But let me just go through it very quickly. The point is that first he's got massive 2a, and then he's mapped that to the Chevalier basis, and so he's identified E11. And then for 2b, for the 2b theory, oops, I don't know what happened there. You know what we do here? Ignore, and probably put it back on. Well, we have our expert here. Thank you so much. Great. So in the 2b theory, everything lives in SL2Z doublets, and this is because it's a non-chiral theory, so you can arrange everything in SL2Z doublets. And these are paired up, no, Schwartz, Ramon, Ramon. And this algebra has a straightforward truncation, which you can think of in terms of string theory. You would call it the orientation projection, type 1b. If you just take oriented strings and map to the unoriented projection. Or you can think of it as taking this global supersymmetry algebra with the SL2Z and just truncate and keep one member of each doublet. So you just break the SL2Z. And if you do this, you get a nice closed algebra, which is unique, and it's the 10-dimensional chiral n equals 1 supergravity. Now we've got another problem. It doesn't want to go forward. Thank you. Okay. So here we come along, and so now, as I said, I know what to do from there onwards. Is once you've given me the 2b algebra, I know what to do. And they had, in fact, already tried this. And I'll tell you what I changed. Schnackenberg and West, they truncated the algebra correctly to D11, and then they appended an abelian gauge potential because they wanted to put in the gauge fields, and that leads to B11 and so on. But it doesn't extend beyond a Maxwell, Maxwell field. You can't really do that. And if you think about string theory structurally, you know from both the heterotic string as well as the type 1 string that the gauge fields are completely disconnected from the supergravity. That's not the way it works. So in fact, it's rather easy to deduce that what you should do is just leave this alone. You've got D11. I calculated these. It's amazingly simple. You just need a little bit of the symmetries, as I said, and you can calculate the structure coefficients without any additional work. So given what they had for type 2b, it's very easy to calculate what the answers are for type 1b. And type 1b heterotic, the supergravity is identical. And this theory is the best known and best studied theory, and there's a reference missing here. It's Eric Bergshoff and Roux. They're the people who calculated up to order alpha prime to the fourth all of the full string theory space-time Lagrangian. So this is the best known theory, and this is the heterotic string. I mean, it's actually known to higher order in alpha prime. So you actually know the massive string states, and you know all of the couplings and so on, and that's been computed by Bergshoff and Roux. And that was another reason why I chose it, is it's very, very explicitly known. So it's a good theory to study. But it's wonderful because in 11 dimensions, in 10 dimensions, once you've got to the n equals 1 type 1 heterotic theory, heterotic type 1 duality, strong weak duality, combined with the quantum-based duality using the type 1a, the T duality type 1a, which has been the subject of a lot of my recent work. It just has so many physics applications. It's just full of physics applications, and that's the main reason why it's such an important theory. This is the one for which everybody studied anomaly cancellation and so on in the early days. This is the one that gives you these n equals 1 theories that Lara just talked about. It's got so much structure, and it's got all the physics. It's got cosmology, it's got gauge theory, non-perturbative gauge theory applications, and the strong coupling limits up to M theory. So once you're at the type 1 heterotic supergravity Yang-Mills theory, you really have a solid starting point for studying all of the physics applications that span string theory. So that's why it's so important. And it's very easy to go back to type 2b or to F theory or anything you would like to. Okay, now the other thing that was important was I pointed out, and which has been pointed out by various other people, what are nice features of West's E11 identification. E11 with the space-time signature 1, 10, or 1, 9, if you come down to 10 dimensions for D11, is unique if you want the supersymmetric extension. So the bosonic algebra only has a supersymmetric extension with the correct Minkowskian signature for spacetime. And in addition, the bosonic algebra, if you keep it all Euclidean, it is unique. It's happy being Euclidean. So those are the two possibilities that are self-consistent. And that's really nice. So it's consistent and unique when you have either Minkowskian spacetime signature or all Euclidean, which is exactly what you want for physics. You want to be able to describe the finite temperature theory, and you want to be able to describe the Minkowskian background. And then you have everything else you add on, which is the branes and so on, and you can do that, but you've got a very good starting point. And as I said, this was the point, is you've got a unifying algebra and a good starting point to study your theory with lots of physics applications. Now, one of the things I wanted to put in here was one of the things that we showed, and this is where the grad student came in. This was the earliest thing that we did in 2000, but in fact, Lara's talk was about these background two-form fields. And we had shown the now string calculations, and in fact, you can even find that in very old papers, but it had not been fully appreciated, Callan et al., as well as Fratke and Setlin, that you can actually calculate string amplitudes as a function of the two-form field for arbitrary field strength. Now, this is great. It covers electric magnetic for the Maxwell, all of the Yang-Mills electric magnetic, okay, as well as the two-form potential, the antisymmetric two-form potential. The Noah-Schwartz two-form potential is the potential that couples to the fundamental string. So it's the most fundamental, potential in string theory. It's kind of like an identifying signature. What else does it do? It makes space-time non-commutative, which is very interesting. So you can try to look for signals, observational signals, on the basis of two things. One is Yang-Mills fields and Maxwell fields, which we know and love. Electromagnetism survives down to low energies. You can even imagine tabletop experiments for that, or astronomical experiments for that. And you also have, the two-form field and non-commutativity. If you could come up with a tabletop experiment of that, and people have actually come up with such a proposal, that's great. I mean, these are ways of testing string theory which are independent of accelerator physics, which I think is a great thing, and I'm all for it, and that's what I used to work on. And I think this is another area, and it's wonderful that we can do these things. So anyway, while doing this calculation, we showed that using the Riemann surface technology for string theory, all string theory amplitude calculations and perturbation theory, there's in fact one boundary condition. You had Dirichlet, which gave you Dirichlet branes, Neumann, which were the original strings, and then you have modified Dirichlet. Modified Dirichlet had not been studied very much. It shows up first in this paper in 1982 by Orlando Alvarez, where he was motivated by a physics question, which is, if I have a Wilson loop and I want to calculate the expectation value of that, then effectively, Ken Wilson years ago had conjectured that this should go as the action of a string. Okay, there's an effective string. However, this computation can, for an exactly renormalizable string theory, which is what the Polyakov string is, Polyakov action is, ought to allow you to study the short distance structure. So if you want to study the physics of string theory amplitudes and gauge theory physics down to short distances, and cosmology down to short distances, which is really interesting because, again, you're studying, like you go back in time, because this is a theory which treats space and time in an equivalence. So we can go back in time and talk about very early universe properties. Short distances and early times, then the action you want to be using, the theory you want to be using is the Polyakov string. And this non-perturbative question in gauge theory has potentially an answer if you extend the Polyakov string path integral with modified Dirichlet boundary conditions. And anyway, there's a couple of other people who studied this. Here, there's one paper in 1986, and then the parts that were not finished in that I finished up with my students, Eugene Chen and Eric Novak. And as I said, a crucial part was using these background fields. The reason the background fields are great is that they make the theory more observable. There's just more observable features of it. You can calculate things like potentials, which you can think about. You can a heavy quark, anti-quark potential or its analog. Okay, so I will carry on and just point out that this shows you also that the generalized electric fills in the last of the D-brane spectrum so that you show that you actually have 11-dimensional electric magnetic duality, which is, again, a nice finish to the fact that you've got a theory starting with E11, and we've pulled that all in. Okay, so I think I've run out of time. So I will just go back to, I think this is my last slide. And I don't have time to tell you about the matrix theory realization, but I've been talking to various people about this informally. It's natural if you have an algebra. The first thing I will do with it, if you ask me if I'm talking about a very small volume of space, which is your Planckian space-time volume that you begin with the Big Bang, or you want to, in fact, talk about the steady state problem, R vacuum, which is non-compact in 4 dimensions and has 6 dimensions compact as far as we know, 6 or 7. How do we end up with that? Well, one way we know how to do that is with matrix models. We take large n limits, and a double-scaled or multiple-scaled large n limit gives us extra dimensions that are non-compact. So irrespective of whether you're trying to solve the steady state problem, which is particle physics, or the cosmology problem, it's great to look for a matrix realization first. And so that's what I did. And I was helped in that, as I said, by the fact that the action, the space-time string theory, effectively Lagrangian out to order alpha prime to the 4th had already been worked out by Birkhoff and Roux. And what I did was I just moved flavor large n over to the flavor large n. So it's not mixed in with the gauge symmetry group. It's not mixed in with supersymmetry. It's not mixed in with Lorentz symmetries. These are all orthogonal to the flavor large n. And this raises many interesting questions, which are only going to find a dynamical answer in the future. It relates to entropy calculations and the initial state of the universe, the resolution of the Big Bang singularity. But one of the things it says is that if you really believe this principle, and we start with this as our guiding principle, then the initial state of the universe has to be symmetric under D11 cross E8 cross E8. Okay, all right. So I'll stop there and leave the rest for questions.